Hello and welcome back to this seemingly never-ending deep dive into the ThunderScope front end. Today we're going to be talking about the bandwidth in 50 ohm mode. And why specifically 50 ohm mode? Well, it's easier for us to analyze that first and then talk about 1 mega ohm mode because that one is tricky. So 50 ohm mode needs a 50 ohm termination. And as we discussed in the gain attenuation video, we actually have the termination in the form of a divider. It totals to 50 ohm, and it's a 5-to-1 divider. Now, why do it this way and not just put a switch way out here with a 50 ohm resistor? Well, if you put it up here, you can just use the normal 1 mega ohm attenuator, and you don't have to worry about different voltage ranges and all of that. The downside is you're now in parallel with all the capacitance that exists in the rest of the front end. So let's say at the input and getting to the attenuator, we have an unavoidable 3 picofarads. And then this path, the 1x path, needs to equal the 50x path in capacitance, which is about 7 picofarads. How does that distribute to the 1x path? Well, we purposely add the 2 picofarads to the about 5 picofarads of the buffer and associated circuitry. Why do we add the 2 picofarads? Well, that's actually something we need for 1 mega ohm mode. In essence, in 1 mega ohm mode, we want to have 1 mega ohm in parallel with a capacitance. And in this case, we are shooting for the lowest capacitance that we can reasonably use with most passive probes, which is actually 10 picofarads. Funny enough, that actually cuts us out of some passive probes, but the vast majority will go down to 10 picofarads. That's quite common in more high-performance scopes. So how does that actually look like, this 50 ohm in parallel with the whole 10 picofarads, when it comes to the frequency response? Let's take a look in LT-Spice. So here's the low-pass filter that is essentially created by putting that 10 picofarad in parallel with our 50 ohm termination. The 3 dB point for this filter is just after 600 megahertz, which, considering our ADC sample rate is 1 gig sample per second, is over Nyquist already. So that's fine, right? I mean, I would still rather design it better from the get-go, but there is also one more catch, and that's a different figure of merit called VSWR. VSWR, or voltage standing wave ratio, is a metric that RF engineers love to talk about. It's basically the efficiency at which power is transferred from a source into a load. And in this case, we are the load. To maximize VSWR, you want to make sure that you are as close as possible to a 50 ohm impedance for a 50 ohm system. And in this case, the 10 picofarad capacitor takes our 50 ohms and over frequency adds imaginary impedance to it, making it not 50 ohms, because unfortunately, imaginary impedances are quite real. This is a graph of the VSWR for this kind of termination. And to put some context to it, 1.5 is what we want to be shooting for. 2 is all right. And here we reach 1.5 just after 100 megahertz, 2 just after 200 megahertz, and we skyrocket up to a VSWR of 5, which is quite bad, at around like 550 megahertz. Here's the VSWR for the circuit that we're using. Note that it stays below 1.5 out to about 400 megahertz, and it stays below a acceptable 2 out to 700 megahertz. The reason it can do this is we actually switch out 2 picofarads completely, which exist in the 1 megohm path to bring us up to that minimum 10 picofarad value for use with passive probes. And it also isolates this 5 picofarads of the buffer and its associated circuitry behind the divider. So that is in parallel with 10 ohms and not in parallel with the whole 50. And that makes its effect on the overall impedance a lot less. So really, there's only that beginning 3 picofarads to contend with. Now that we finished talking about the termination, let's look at the active devices in the front end. First, the buffer. This thing has a bandwidth of 3.1 gigahertz, so it's probably not the limiting factor here. The programmable gain amplifier has a bandwidth of 900 megahertz. Now it also says it's got 1 dB of peaking, and as you know from the low frequency response video, that much peaking can cause some really weird stuff in the time domain, so we're going to have to deal with that later. The ADC is our limiting factor, both in terms of analog performance and also in terms of sampling performance. So the maximum analog bandwidth of the ADC is this full power bandwidth of 700 megahertz. The maximum actual sampled bandwidth by Nyquist is going to be half of the sample rate, so 500 megahertz. Now we like to use like an anti-aliasing filter before that in most scopes, so we basically call that 350 megahertz. Now, the thing with this ADC is it's interleaved. So that is the bandwidth on one channel. The bandwidth on 2 channels is roughly half that, so 200 megahertz, and the bandwidth on 4 channels is 100 megahertz. And then if you go into 12-bit mode, you have that still. So editor's note, I switched to sample rate here. If you want bandwidth, like I was just saying before, divide by 2. It becomes kind of like 500, 250, and 125. And the reason it's not 640, it's 500, is because we bit stuff 12 bits to 16 bits. Because CPUs like when things are aligned on byte boundaries. Now, this doesn't stop you from sampling over Nyquist, which I will be showing you soon enough. But in terms of how you would use a normal scope, that's kind of your limit. So with all that talk about increasing the bandwidth, why would we ever want to reduce the bandwidth? Like everything else about this design, it's a trade-off. So the first trade-off here is in power draw. We shave a little bit of current off of the buffer by using a even lower power mode than what they recommend for low power. And in that case, it's 24 milliamps per rail versus 17 milliamps per rail. And that's because of this R bias resistor right here, a 100K. Now they have graphs for this, and presumably 100K actually gets you a 3 dB bandwidth of about 650 megahertz. And surprisingly enough, that's fine. That's fine because of the second point. Why would you want to reduce the bandwidth? And that is peaking. I told you it would come around. So this is the measurement we got when it was, I believe, 30 ohms in series. And I think it was still with 100K. I'm not quite sure. But as you can see, it's really bad. It's like over 3 dB of peaking before it comes back down. But it's a lot of bandwidth, right? If you measure minus 3 dB, it's like over here somewhere. So how do you fix this? Well, you can basically turn down the bandwidth of the rest of the system, or you use a different trade-off to your advantage. You trade off bandwidth to improve peaking, but also to improve your maximum input voltage range. And that's why we have two 30 ohm resistors right here. Now you could basically keep stacking those, but the problem is eventually you run into the extra like parasitics of having a bunch of those resistors. And if you use high value resistors, well, now you're burning a lot more power in those, and they have to be bigger in order to sustain that power rating. So it's all trade-offs, whole way down. Let's actually take a look at a few different ways you can measure bandwidth. Right? So I showed you one, which is just to put it across a scalar network analyzer or a vector network analyzer. And that basically gives you a bode plot, right? But a spicy high frequency bode plot. So that's one way, right? You have your bode plot, and you just sweep one frequency the whole way down, right? But then you have a different way of doing it, which is to use a wideband noise source, right? So you basically, in the frequency domain, that's not frequency, that's frequency. And then that's like amplitude, yeah, dB. So you basically have a wideband noise source, which gives you a consistent amount of power at each frequency, and that way you can kind of just take an FFT of it and see your response at a glance. The other way of doing it is by looking at the rise time of a very sharp pulse, right? So that rise time from 10 to 90% relates to bandwidth. There's a rule of thumb factor there of 0.35 over the rise time, and that gives you bandwidth. So now that we know how to measure bandwidth, let's measure some bandwidth. So the first thing I'm going to do here is the wideband noise source approach. Now I don't actually have a proper RF wideband noise source, so I'm using my function generator, which can go up to 120 megahertz, which you'll soon see. Let's do an FFT on channel 1. Let's turn off these points. All right. And then one more thing. Going to go direct connection, and then we're going to turn on 50 ohm mode, just so we can get a better look at the actual response, and we're not driving that input capacitance directly. And yeah, there you go. Let's zoom in some more. So yeah, that's pretty flat. Looks like it really drops off around here. And I, again, suspect that's the function generator giving its rating is 125 megahertz, and that's a 3 dB point rating. So probably we're just looking at this region up to 100 megahertz, which, yeah, looks reasonably flat. Now, this isn't the most accurate measurement. Let's take a look at the interpolation and how that works. So by disabling these two channels, we get into two-channel mode, which goes up to 250 megahertz. Now you start seeing some interleaving spurs here, 250 megahertz and 125. Those are all just fractions of the sampling rate. And then by turning off channel 2, we go into single channel mode. And now we actually go up to 500 megahertz because that's our Nyquist frequency in single channel mode. And yeah, that's wideband noise. let's try a pulse generator next. I'm using a Leo Bodnar pulse generator, the BNC variety. This one's obsolete now. There's a new one. But it does a 40 picosecond rise time pulse. So way faster than even our front end bandwidth. So that's perfect for this test. Let's take a look at these square waves. Now this is 50 ohm mode because it's a 50 ohm output pulse generator. Let's take a measurement here of the rise time. So yeah, this measurement can't make heads or tails of this because, well, that edge is literally one sample a lot of the time. So yeah, let's take it that the bandwidth is way higher than what we can do on 4-channel mode. So let's turn off 2 channels, see how it looks like then. All right, now we're starting to see some things, but still, that's, yeah, pretty much one sample there. Maybe 2, I'm not sure if that's 90. Oh yeah, here's the rise time measurement. Let's actually just change that. I can show you how to do that. You go to the filter graph. This is a very neat idea, the filter graph. So the data from channel 1 is going to this rise time measurement. Now, if you right-click it, go to parameters, you can set it up to be the 9010 that we mentioned for this kind of rule of thumb measurement. And, oh, there you go, 3 nanoseconds, which is, again, very close to the it would be the 2 nanoseconds for 500 meg sample per second sampling. So that's like a 1.5 samples. Okay, let's try single channel mode. There we go. That's nice. So you can see the response a little bit there. That's a nice critically dampened. Yeah, that looks good to me. And now we actually are consistently getting a rise time of a sample and a bit. So yeah, for 350 megahertz, which is all we can, well, 500 megahertz, because I don't have the anti-aliasing filter on. So for 500 megahertz, which is all we can measure with the ADC, this is perfect. Now let's move beyond the limitations of the ADC and basically just use coax cable to grab the output of the analog front end directly and do another measurement with a scalar network analyzer to get the true response of the front end. All right, so here's the setup. I'm not going to be doing this part live because there's a lot to cover and I don't want to make this video another like 20 minutes long. So basically, here's the scalar network analyzer. It's a signal hound with tracking generator. And the little board on the left there is a Balun, which converts a differential signal into a single-ended signal. So that should be essentially what the ADC sees coming out of the PGA. Here's the little UFL pigtails going to those SMAs. I can't recommend these at all. They're really, really finicky, and yeah, maybe I just need to get better ones, but it's been a real pain trying to get a stable measurement with these. Yeah, maybe I need slightly larger connectors than UFL on the back here, but yeah, that's always been annoying. Just a little pro tip. And as a reminder, we have in the signal path changed this capacitor to 1.2 nanofarads, and this resistor here also changed, but that's not in the high frequency signal path, so we don't need to consider it. This is a measurement coming out of a test board. This was right before Rev 4, so we expect to see something quite nice looking like this. And you know what they say about having high hopes? This is not great. That's a lot of peaking, and there's like 2 peaks for some reason. An editor's note, the reason you don't actually see this show up in the other tests is because of the Nyquist frequency of the ADC. In single channel mode, you basically get 500 megahertz. So you capture a little bit of that first peak, but it's not really that impactful in terms of what we can see. And that's also because we're not using sin x on x interpolation here. We're using linear. And that's also why I did not use the rise time to bandwidth calculation, because that's invalid. Because not only are we not trying to represent perfectly a signal, which is what sin x on x does, and that assumes if the signal is actually fully below your Nyquist frequency, which it is not. And then on top of that, we also just don't have all that much bandwidth below Nyquist. So yeah, that's why it looked really good on those other metrics, but when you actually test it across all the frequency range, you get this. And right, like I could of course just slap a filter on there and call it good enough, but really I want to make this front end in the same class of, like, you know, 1 or 2 like classes of scope higher than this, just because I want that trust in the front end, and I also want to be able to iterate and make more scopes with it, and also make a front end that is useful to as many people as possible. So if you are making a scope, I want to make sure that this front end has a chance of kind of fitting your specifications. So the wider the bandwidth, the better. And that's why I'm continuing to optimize this. So we'll have to think of a solution. As I mentioned before, there is the R-bias resistor on the Buff 802. That's being basically almost completely on one side of the spec. It's mostly specified at the 2 values of like full bandwidth and reduced current. 100K is like really, really low. So I figured, okay, maybe we are being bitten by that. And it does improve this rightmost peak a lot, leftmost peak a little bit, but that's not our solution. So we got to thinking about the circumstances behind this measurement, and I realized that this is coming straight out of the buffer. So this isn't actually out of the PGA. So how did I connect the buffer? Well, I connected the buffer with a series resistance of 50 ohms to match the line and into the scalar network analyzer. So I figured, okay, we are going to need some sort of series resistance here. If you look into the data sheet, it will peak when driving a capacitive load, so that made sense to me. And 100 ohms was way, way too high. So I tried 50. And that's more like it. As you can see here, our 3 dB bandwidth is lower, and that's to be expected when you add a resistor in the path, but we have essentially no peaking and a nice smooth response, so that looks good. Another thing to watch out for is with PGA like this, there are actually 2 different amplifiers, right? A low gain and a high gain, and then a ladder attenuator. So the actual response is going to change over every single gain range. Here's just a selection. This is the highest gain range with the 30K R bias and the 50 ohm series, like output series resistor. And then here's a slightly lower gain range, lower still, lower, 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 and lowest. So if you notice the bandwidth, marker 3 here, the lowest gain range has the lowest bandwidth, and the highest gain range has the most peaking. And that's something we want to look at different values to solve. So in black is a 100K R55, so the original kind of bias value, and 50 ohm R56, which is that series resistor going to the PGA. All these are 1.2 nanofarads C26, because quite some time ago I proved to myself that the kind of impedance profile of that capacitor doesn't matter all that much here, so I didn't think we would need to change those, and it looks like that was correct. So you can see there's a big difference between the 50 ohm series and the 33 ohm series resistor. In this case, the 50 ohm has less bandwidth, but it has pretty much no peaking, while the 33 ohm has this peaking up here, which is actually unacceptable. That's too much peaking. So basically, it's a trade-off, right? If you do a resistor somewhere in the middle, you're going to get a bandwidth in the middle and peaking somewhere in the middle. For our purposes, I think we can just accept the lower bandwidth of 50 ohm series resistor in order not to have that peaking. And the ultimate bandwidth rating is going to be on the lowest gain mode. So if we take this as our worst case peaking, which it is, 50 ohm has essentially none. And then you can see that it has 3 dB bandwidth of about 600 megahertz here versus 700. So we could get 700, which actually does match the ADC's full power bandwidth, but then we would have to contend with some peaking, while if we go with 50, then we can get 600. And that also lines up nicely with the inbuilt bandwidth limits in the PGA, which are, for the higher frequencies, are 600 and 750. So if we turn on the 600 bandwidth limit, then we should essentially be able to kind of normalize a lot of these gains to be the same bandwidth. It won't affect what's going on up there, but at least we can have a more consistent bandwidth across all the ranges. Oh, and that's it for my little slideshow here. Yeah, I thought it was very interesting tuning this. And yeah, just another aspect of such a long-term project where you have like all these different test boards and all these different revisions. When you test something and you don't have enough documentation, which, yeah, I'm definitely guilty of, you forget things like, oh, like there's a series resistance between the buffer and the PGA. Thankfully, I did include this resistor here because I thought, okay, we may need to tune this, and turns out, yeah, we do. So yeah, 50 ohms there, and I think I'm just going to go with the datasheet approved kind of. It's not 30K. I tested with 30. It's actually like 35.7. But I think I'm just going to do that just because that way I can use a lot more of the datasheet specs versus the few graphs that actually mention running it in 100K. And then we can eat the current difference, because with the custom FPGA module, it's going to use a lot less current as a whole than using the Trent's electronics modules that we were using. So that's no longer as much of a concern. So yeah, that's the frequency response and bandwidth in the 50 ohm path, which is like already a whole video. And then we're going to get into the same thing on the 1 megohm path in the next video, which is going to be really fun. We're going to talk about scope probes and this attenuator and how that works in that video. So stay tuned. Thanks for watching.